So some techniques on how to make deep learning inference faster. Um, so without slide, this is hard to describe, but let me give you like a high-level idea verbally. So when you think of, let's say, the how to speed the inference, you can think of, let's say, the using lower precision or fixed precision, such as integer 4 or integer 8. Or sometimes you can think of pruning to make essentially neural network smaller. I mean, smaller means faster. So if you can prune out more neurons, essentially you can make your inference faster on GPU kind of devices. And sometimes you want to use some kind of a graph optimization technique. Let's say that if you have multiple layers in your inference computational graph, you want to apply kernel fusion so that you can have a fewer number of layers. Hopefully, it can reduce the total computational resource limit. So you can think of those techniques essentially to speed up the inference on GPUs. But I would argue that these are all static techniques. You will do type conversion offline, then you will do pruning compression offline too, and then you will change and optimize the graphs offline too. So these are kind of offline techniques, right? Of course, I'm not saying that offline techniques are not good. What I'm saying is that there can be online techniques which can be complementary to your offline techniques to make an inference even further scalable. So that's the topics that I'm going to cover in this talk. So I think the slide is still being sent there. So what kind of techniques can we do to make a deep learning inference faster online? So I'm going to, so in general, if you think of a general computer architecture, what do? You can apply all the offline compiler techniques to make your program faster. But during runtime, you can enjoy cache locality, or sometimes you can have a better, smaller number of paging fault, right? These are kind of offline techniques we are already using to speed up the program execution on a conventional computer. So what I'm going to show here is that maybe it is possible that we can apply similar techniques from deep learning perspective to speed up the inference engines on GPUs. And the one technique I'm going to propose is that we can share compute across the multiple models. The second technique is how we can reuse the already computed result for prediction input. So the second technique is essentially about how we do caching for deep learning. JRM, I think I need to wait here because I cannot make.
Yeah, you could try sharing your slide again.
Right? Yeah, let me try again. Yeah. I don't know why it doesn't work here.
Yeah.
So I don't know whether anything is appearing there.
Hold on. Let's just hold on.
So just as a recap, so I'm going to present two techniques that really proves that it's possible to do dynamic optimization for deep learning inference. That's like a key takeaway I really want you to get out of my talk.
Maybe you can send your slides and we can try to share our screen and you can talk.
Yeah, I already sent to JRM. Okay. JRM will have it in a second. So okay. Let me stop sharing here because it doesn't work for me anyway.
Yes, yeah.
Mm-hmm.
Okay, I got your slides. Give me 1 second.
So his file is kind of big because I have some live, some video demo there.
Yeah. Okay.
Yeah, I should have made
That's
it.
the reason. Yeah. Okay.
Yeah, I should make it like much smaller. I mean, I didn't anticipate the hiccup here.
Okay. So let's see this. Okay. So Snow IBM.
Yeah, the 0522. Yes. So you can go to page number 2.
Got it. Hold on one second. Just tell me the slide.
Yeah.
Do you want? Oh, okay. Hold on.
Yeah.
Sorry.
Yes. So you can switch to the display mode.
Yeah. Hold on. Oh my goodness. No. Hold on.
No, you can go to the swap display over there. You can.
Yeah. I know. Hold on. Give me one second, please. Okay. And yeah, which slide?
Okay, good. Thank God. So the slide number 2. So this is what I have been talking about. So there are like many static techniques to speed up the inference, but here I'm going to show that actually it's possible to do dynamic acceleration of an inference engine because this is a specific this is in specific context of a deep learning inference. So let's go to the next page. So there will be animation. Next page. The first technique is that so the first technique here I'm going to present is that how we can share the computation across the multiple models. So this is the work we presented in iClear 2020. So when somebody mentions, let's say, the sharing computation, that means that essentially there are more than one model running on your system. So first I want to make sure that actually in the old scenario, we like to have a multiple models running in parallel behind a single source of input. So let's imagine that we are building some kind of intelligent grocery shopping for customer. The customer already has a camera, and the camera is capturing many information. Captures customers, products, aisles, everything, right? But behind the camera, if we have to run only a single model, that's a waste of information we are getting from the camera because there are tons of information. We want to extract as much information possible by running multiple models behind a single camera in parallel. So this is a typical use scenario in the real world. For example, in grocery shop, we want to have a model for loss prevention. We want to have another model to understand associated activities, and then we want to have another model to check the inventory status, right? So essentially, we will have a single input, multi-output kind of a scenario in real world. To enable this kind of a scenario, we can have like 2 approaches. One approach is based on transfer learning. So for a given generating model, we can perform transfer learning to build one model for loss prevention, another model for next test, and so on. So this is one approach. But the other approach is that essentially we are getting all the feed from single camera. It is possible to develop joint representation for all the models and then have a different kind of a backend to deliver individual tasks. This is a multitask running approach. So we can see that there are 2 possible approaches. And I'm going to talk about pros and cons of these 2, and then how we overcome the cons of these 2 approaches to make like a different the style of, let's say, the multitask running. But imagine that the customer is very satisfied, and you can click JRM here. So customer is very satisfied, and then he want to add additional model to understand the customer insight. In this case, if we use transfer learning, this becomes essentially another like individual transfer learning. But if we have to use a multitask running, and if we have to use an existing joint representation, this becomes a lifelong learning. So next page. So essentially, we can solve the real-world AI problem, multi-input, single input, multi-output problem using either transfer learning and then lifelong learning. But each approach has a pros and cons. The pros of transfer learning is that this is easy in terms of flow because everything is independent. Just you will do n number of training to develop n number of models. The problem is that once you have n number of models, each model is essentially as big as your source model. Then each model will require the same amount of storage, right? So in terms of computation, this will be very expensive. If you have to deal n number of models, and then training time will be also big because each model is big, essentially. Not to mention the storage cost to keep all the models. If we use, let's say, the lifelong learning approach using joint representation, the good thing here is that now you have some kind of sharing appearing here. You will have a single joint representation that can be reused for all the models. So your parameter efficiency is very high. Accordingly, your computation efficiency will be very good too. The only problem here is that we are not sure whether this joint representation is useful for the all n number of tests, right? Unless you have all the, let's say, all the data sets, developing a perfect joint representation for the future task is not possible. That's the reason why, in many cases, the result out of a lifelong learning will suffer from accuracy loss. So that's the reason why we are taking like a different approach in our paper in terms of compute sharing. So to motivate the problem from mathematical perspective, I want to introduce like a simple model. So in this model, let's imagine that we have a function f, that takes in x and w here, and then now we can think of some kind of a deep learning pipeline with L plus 1 number of layers. So the mathematical meaning of transfer learning here is that starting from the current parameter set w, essentially we want to find delta w in a way that the function f can perform different tasks, right? So that's essentially the concept of transfer learning. But if we take the Taylor expansion of this function, the bottom function, then we can easily see that the very first term of this Taylor approximation is essentially the original function from the source model. And then you will have some additional terms from the first order or second order factor. So essentially, what we are saying here is that instead of doing transfer learning, actually it is possible that we can reuse source model as it is, as long as we can compute the gradient for the new task and then deviation in terms of delta W. So if we can compute those two things very efficiently, essentially we don't need to do transfer learning. We can approximate our target function as a Taylor expansion. And then the question is that how we can compute let's say a slope or like a sensitivity of our target function. If you take a look at the actual deviation, the derivative of the function against, let's say that layer K, you can see the canonical product of two terms. You have, let's say that, can you go back to slide? So you have, let's say that WL to WK plus 1, then you have a canonical product, and then you have a K minus 1 all the way to X. But you can now see that the second term is already computed from the source model because source model is a product of from X to all the way to L. The question is that can we reuse all the partial product of a source model to approximate our target function as a replacement of a transfer learning? That's the key idea in this paper. And then now you can see that if this is possible, actually we can reuse the first term for all the target functions. Let's say that I have one single model, I have n target functions. That means that I can reuse the source function n times for n number of Taylor approximations. That's where the compute sharing actually happens. And that's how the inference can be really accelerated using our technique. So next page. So for the sake of time, let me speed up a bit. So the key idea here is that we want to reuse the features, intermediate features from the source model, because we know that it is needed as a part of a tail expansion to approximate our target functions. And then source model can be used multiple times for n number of target functions. That's the key idea in our technique called SNOW. And then I'm going to present very high-level details of SNOW technology, and then jump into the result. So this is a kind of a high-level overview of SNOW architecture. So as I described, we want to reuse all the intermediate features of the source model across n number of models, because from the tail expansion, we know that they need it in terms of approximation purpose. But question is how we deliver the information from the source model to the n number of target model. That's what we are doing in SNOW architecture. And then for the proposal, we are proposing something called the channel pooling layers. I wouldn't get into the details of these channel pooling layers. If we are interested in how it is done, I really suggest to go for our iClear publications. But essentially, what it's doing is that dimensional reduction. So if we have many channels, but we know that we don't need all the channels for all the tasks. So what it does is that it will actively select useful channels, subsetable channels for particular tasks, so that we can make our, let's say, the target model size much smaller. So from the, let's say, execution perspective, if you have an n number of models, we are going to have a source model always running and generating intermediate features. And then target models, we subscribe those generated features and then reuse it along with its own local features to deliver the output. So that's how it is done in SNOW. The next page. So this page is really to make idea very crispy. And then by comparing it against a knowledge distillation. So on the left side, we have a knowledge distillation technique. On the right side, we have a SNOW technique or a knowledge subscription. So in knowledge distillation, we know that we will really capture the essence of a teacher model and then transfer it to the student model. But once the distillation process is over, we don't need to teach anymore because the student has learned everything. It knows everything. It can produce output by itself. But in SNOW technology or knowledge subscription, we need a teacher all the time because we will reuse whatever teacher generated in the student model. So that's really a benefit of SNOW technology. So in many cases, I take the following analogy. So knowledge distillation is like a closed book exam. So before taking exam, you have to understand every contents in the book. And then you cannot take the book to the exam because you need to do by yourself. But in knowledge subscription, this becomes some kind of open book exam. So instead of, let's say, memorizing all the contents in the book, we are asking to memorize the page numbers only. So as long as you know the page number, you can go to the book, open up the book page, and then use the information to solve your problem, right? And then single book can be shared across multiple students, but each student will have a different index numbers, right? So they will just use their own index numbers to look at the book, to read the book, and then use the independent information for their own purpose. That's how knowledge subscription can really speed up the computation and then make a model size very smaller because now we only need to memorize the index numbers only. The next page. I really hope that this can make our idea very clear. So we compared our technique against different kind of transfer learning techniques. I mean, these are the kind of illustration of different transfer learning techniques available in the literature. But for the sake of time, I like to go to the next page to really highlight the benefit of knowledge subscription here. So we combined 5 different target tasks using our SNOW technology and compared it with the other transfer learning technologies. Let's say that we will do transfer learning 5 times to get the best performance, best accuracy out of an existing conventional approach. Next page. And this is kind of a high-level view So from the given pre-trained ResNet 50 and the ImageNet model, we will, and then this model serves as a teacher. We will subscribe all the intermediate features and then using our channel play technology. And then pooled features will be fed into individual models. Subset goes to food, another subset goes to action, another subset goes to cars, and so on. In total, our model, total model size, model overhead is only 6.3% of less than 50, meaning that to run, I said that 5 models, I need a copy of less than 50, and then each, let's say the sidekick needs only 6.3% of less than 50, instead of having 5 copies of less than 50. The next page. So this is a performance number. So I like to spend some time to digest this figure here. So JLM, you can turn on the video here. That's the reason why the copy was so slow. So on the left side, you can see the graph. The graph has 2 axes. On the x-axis, this is throughput, the inference throughput. On the y-axis, this is average accuracy across 5 tasks. So there are many different kind of technologies here. Some are very fast, some are even faster than snow, some are very slow. But some cases it suffers like a high accuracy loss. Sometimes it has a very good accuracy loss. Now we can see that snow is sitting on the Pareto corner of a trade-off, right? So its accuracy is as good as expensive approaches, which has a very terrible throughput. But it is as fast as a very lightweight approach, which suffers from accuracy loss. The benefit here is that we can make a model size and then computation execution very fast by sharing a lot of computation across many models. But we don't lose that much because the knowledge subscription doesn't do any approximation. It doesn't require any joint representation. That's the reason why student technology is a kind of a way to speed up inference by using compute sharing concept. So next page. So I really hope that we can use compute sharing to speed up the inference. But the second topic here is that now I want to show a case of caching, using caching technology to speed up the inference. So as a motivation, I like to take an example of a human vision. So in human vision, it is very well known that human eye works together with the vestibular systems in your eye. So when you rotate your head, your eye will rotate accordingly as well, but you will remember how much you rotated your head. Was that 10 degree, 20 degree, or like a 5 degree up and down? It remembers everything. But once you have a look at the scene, and then turn away from the scene, and then go back to the original scene, now your processing speed is much faster. Because you just have seen the scene. You understand all the objects, all the colors there. So by looking at it again, your computation speed will be very fast. And this is already known and a well-known studied subject in other domains, like a neurology domain. So you can see the references on the bottom. So idea here is that if that's the case, can it mimic the same effect using our, let's say, the hardware technology? And then my answer is yes, it is possible. And then how do I do that? By using the accelerometer and the GPS on your phone, and then using cameras on your phone. By combining these 2 things as a multimodal AI, we can prove that actually we can really speed up the deep learning inference as well. So next page. So as I explained earlier, once you look at a particular scene, you already have all the understanding in your head. So by looking at that again, you don't need to interpret everything because it is already done there. So by mapping that kind of a concept to our mobile phone, what is happening is that you take a shot, but you move the phone a little bit to the right. So that means that majority of space has been already captured in last inference task. So you only need to worry about like a delta area in the image. The question is how do we understand delta? Because the phone doesn't have the concept. But fortunately, in modern days, most of mobile phones have something called the accelerometer. So accelerometer actually captures your acceleration of the phone, and then by doing let's say the double integration, actually we can compute like a physical world displacement. So by combining your computer vision technique and then sensory signal, actually we can reuse the last convolution result in the following scene because we know that it has been already seen, and then we know that like the displacement in the image, so we can reuse like computing result again to speed up the inference. The next page. So this shows like how accurate it can be by computing the displacement using accelerometer. And then according to our measurement, it is known to be very accurate, and it is reliable enough to be used in deep learning inference to really like cache in the last inference result. The next page. So we measure like how much overhead we are getting, because if we use like additional signals and overhead is very high, then that doesn't make sense in terms of deep learning acceleration. But fortunately, we found that like computing displacement using accelerometer takes only like less than 0.5 millisecond per frame. So this is very affordable. But if we use a more expensive techniques, let's say the MPEG-4 kind of caching techniques, it takes over 150 milliseconds. So this shows that using hardware to capture the displacement is very affordable and then has a high potential to accelerate the deep learning. So we applied this technique to really see how much gain we can get from inference on the mobile phone. So if we use AlexNet for object detection engine on the mobile phone, we found that actually we can have a 2x improvement in terms of training the inference throughput. Okay, next page. I think we are getting the end of the talk here. So this is a conclusion. So here, what I'm proposing here is that the deep learning, accelerating deep learning inference has been done in many directions, but existing arcs are mainly based on static techniques, like type conversion, like a pruning compression, or static graph optimization. What I'm saying here is that actually now we need to look at the different aspects of acceleration technology. And then sharing is one option, caching is another option. I'm pretty sure that there can be some option. But by looking at like a dynamic aspects of a scalable inference problem, I'm pretty sure that we can have a much scalable and then much high quality inference for the actual customers. I think that concludes my talk here. And then I'm taking any questions audience may have. Thank you.
Thank you, Minsik. Yeah, please ask questions to Minsik now. Please go ahead.
Hey, Minsik, this is Ashish here. So thanks a lot for your talk. Very interesting. I had a question about the trade-off between accuracy and inference time, which you showed on one of the charts, right? So
yeah,
the technique which you proposed is looks like it has a best combination of these two. I was just curious, are there any hooks into the scheme wherein if somebody wants to trade off accuracy versus the speed, can you do that?
Yes, it is possible. So I don't know whether JRM can go back to the slide here. But if you recall the Snow architecture image that I showed there was like something called the channel pooling layer. And then I said that like what channel pooling layer does is dimensionality reduction. So if you have a very high level of reduction, meaning that you will squeeze out a lot, that means that you will have a smaller number of features coming from the teacher to the student. So in that sense, you will have a less accurate model. at the end. But because you are now like squeezing out a lot, your computation efficiency will go better. On the other way, if you subscribe more and more features, there is a higher chance that your accuracy will go up because now you have more information to leverage. But in return, but at a cost of a higher processing time, because you have a more channels to process. So we have a hook to make a very good smooth trade-off between accuracy and the performance. I hope that this answers to your question here.
Yeah, it does. It does. And I had one more, which is so you also motivated this by saying that if you have one more additional task, the common representation scheme fails, right? Because you have to again
Yeah.
come up with the common representation. So is this scheme flexible enough that you can add additional tasks without
Yes.
retraining on the
Yeah,
previous
because we don't have a concept of, let's say, the joint representation. All it does is that we will have a generating model generating the feature. And then it is up to student to pick which feature you like to subscribe, right? So in our case, all the training for individual model is independent because they don't share anything. They share teacher, but teacher runs in an inference model only. So your question to an answer to your question is we don't have a joint representation. But that's the reason why even though you append more models in the future, it doesn't affect any other existing models and then new upcoming models because they are all running independently.
Okay, thanks, Minsik.
Yeah.
Good. Any more questions to Minsik? So Minsik, I have one question. So
Yeah.
we're talking about sharing the channel pools from the source model and to the delta models, right? During during inference time, right?
Yes.
Yes. So do we know for these different tasks what are the right channels to share between the two?
So yes, we know. It's like that is determined during training. So I didn't go into like details of their process here for the sake of time.
Right.
But when you do training
Right.
against a particular source task, the
Right.
channel pooling layer will learn
The weights.
which channel to subscribe for task A, which channels to subscribe for task B, and then they can be all different subsets.
Okay.
But you will be learned during training time. And then once the training is over, we can have a static mapping from source model to the data model, so the inference does not so inference can be done without any channel pooling layers.
Okay. Okay. Yeah. Just by listening to your talk, which is very interesting, I just came that there is some type of, I will not say parallelism, but some type of connection with these attention mechanisms in which you talk, in which what they do is that you maintain from the encoder all the embeddings and you only look at the embeddings which are useful for your task, right?
Yes.
Yeah.
Yes, that was a very good point. So channel pooling layer does a dimensional reduction, and the attention mechanism can be one way of doing that. So we have a comparison between different kind of channel pooling techniques, and then we have something different from attention-based mechanism. But definitely, attention-based mechanism can be one way of doing this. But for details, you can email me or you can read our paper.
Yes, sure. I will. Yeah. Thank you very much, Minsik.
Okay, thank you.
Thank you very much. Okay. Okay, great. Good. So now next we go